I'm Kyle here at the Institute of Flight, and we're doing the Oriented Molecules Lab today. We're going to measure the behavior of some pieces of plastic. We're going to start with a hypothesis about whether or not these gallon plastic bags will behave the same in either direction we cut them. We're going to end up with strips like this that we're going to test in tensile strength, which means we're going to be stretching them with our hands, really. And we're going to try stretching them fast, and we're going to try stretching them slowly and see how they behave differently. We're going to use our instructions and procedure sheet from the challenge online. And there are some other instructions on the challenge as well that have to do with how you'll submit your results. That means taking pictures of the samples and also correctly labeling your samples and taking precise measurements. So you can see I have one strip right here, and I might stretch it quickly or slowly, and it's going to have some sort of behavior as I stretch it, something that you're going to measure. And we're going to get at the end some total elongation. So let's say I stop here, or maybe it fails at this length. We're going to measure its final length as compared to its original length. And you can see up there we've got written our percent elongation equation, which is final length over original length. So if the final length is in centimeters and the original length is in centimeters, then we get some dimensionless number. And we're going to do a couple samples fast, a couple samples slow, and compare them both for the direction that we cut them wide to the bag, which will be horizontal strips, and tall to the bag, which will be vertical strips. We're going to see if those two orientations of the plastic are any different from each other. Let's get started. So on our materials list, we've got our plastic bag. We've also got our scissors that we're going to use, permanent marker for labeling things, masking tape for also labeling things. You're going to use maybe a camera or your camera phone to take pictures of the samples of that you stretch to show off your results a little bit in the challenge. Probably use that as the thumbnail for your challenge. You're also going to need a pencil and note paper. And I'm going to be doing my notes with the permanent marker instead, so they're a little bit more visible today. And then we also need measuring tools. So I'm going to use a ruler. If you're in the makerspace or if you're at home, feel free to also use a tape measure. You do not have to, though. The ruler will cut it, though you may have to measure in multiple steps. Okay, so where we're going is basically something like this. You can see I have a plastic bag that I started to cut up, and these measurements are not very precise. So we're going to take precise measurements instead. And we've got some in the horizontal direction, which we're going to call wide, and we've got some in the vertical direction, which we're going to call tall. Also, these lines need to be straight with each other. So let's do that right now. So if I go ahead and I start measuring my strips, I can see that my plastic bag's a little over 10 inches across. So what I'm going to do is divide that in two, and I'm just going to make 2-inch measurement differences right here at the bottom. 2-inch marks, 6, 8, and 10. Notice I'm staying a little bit away from the seams at the edges, which is useful because we're not going to use those seams. They would obviously make some of our samples different from each other. We want them to be the same. They want to be different tests, but the same. And if we make them the same, then they can't have those different textures in them. At 10, at 8, at 6, 4, 2, and 0. So now we've got one side, and this is going to be what we call tall. So I'm just going to put, let's do T1, T2, T3, T4, and T5. And you can see I'm not writing it in the center where most of the stretching is going to happen. I'm writing it at the end where I'm going to be holding on to it, because there is some chance that the solvent in the marker could change the behavior of the plastic, and we always want to eliminate as many variables as possible. All right, and then I'm going to go ahead and draw my lines. And we don't necessarily have to watch all of this. So this is probably where we will fast forward. Okay. Once we've done that, we've got to go to the other side. Now, the point is to see, as you'll remember, whether the plastic behaves the same in both directions. So on the opposite side, we're going to do it the opposite way. And you can see these plastic bags are pretty square. So if you're doing this at home, you'll want pretty square plastic bags so that you can get the same stuff out of both sides. So once again, I'm going to do 10, 8, 6, 4, 2, 0. And I'm going to label these wide 1, wide 2, wide 3, wide 4, and wide 5. I'm going to do the same thing down here. We're also going to give everything a moment to dry for the permanent marker here. All right, so we've got our sample looking like that. Okay, now we're going to cut off the parts that we don't want. So we don't want the seams on either end, and we don't want the zipper, certainly. That's going to behave differently. So we're going to start by just clipping that. And if we've done this correctly, none of them will need any of those parts. So you can see I've got a clean cut where I mostly slid right there. If we've got jagged edges, then those are all places where a tear can start. And that means that we've kind of changed the behavior of our sample. So we're going to avoid sawing at it. So once we're done doing this, we won't be able to visually tell the difference between the samples that we cut in the wide direction versus the tall direction, the vertical versus horizontal samples. And that's why we've labeled everything. All right, so at this point, hard to tell the difference between our samples, which is why we have them labeled. And we're going to go ahead and separate them from each other. I'm just going to do a couple examples here because you're going to do the actual experiment and see what results you get. Okay, so here's our wide sample number 1, or number 5 in this case. But what we're going to do is use our number 5s or our number 1s, you can make that decision for yourself, as our test sample. And we're going to test it like this. We're just going to make sure that the behavior is what we think. So if I take this one, this wide sample, and I stretch it as fast as I can, it tears pretty quickly. But it doesn't tear like a piece of paper, and it doesn't shred like a piece of wood, and it doesn't even tear like a piece of metal. So what we get is this stretched out region right there in the middle, and I didn't maybe tear that quite as fast as I could. You're gonna put your full strength into it and tear a couple of them as fast as possible. And if you're following the instructions, you'll also tear a couple of them as slowly as possible. So I'm gonna start by actually measuring our widths here. So we've got wide 1, and we're gonna go ahead and measure that. And we'll find that after all that cutting, let's go ahead and do millimeters. It is 25.5 long. And if we want to just make sure we get all the results, it's about 4.5 centimeters wide. So 25.5 centimeters by 4.5. Okay, we're going to do that for each of the samples. I'm going to go ahead and do that for tall now. So let's, so you'll make a table with all of them, etc. And you'll just do starting dimensions and ending dimensions. So if we assume that wide 5 was about the same, let's go on to actually tall. Let's just do tall 1, tall 2, tall 3, tall 4, and tall 5. We'll do start and end. And you'll notice you're also dividing these into one test strip each. And then you're also dividing them into the fast and the slow tears. So in this case, let's go ahead and do wide 5 as a slow tear, or as a fast tear, as we just did. We'll do tall 5 as a slow tear. So you'll label those as, let's do like this: fast, slow. Okay. So you can see this isn't maybe the most artistic one here, but we've got our test strip right there is number 5. And then we've got number 1 and 2 are fast, 3 and 4 are slow tears, 1 and 2 are fast tears, 3 and 4 are slow tears. And we're going to record the dimensions for each of them before we tear them, start, and after we tear them at the end. Okay, and here we've got test strip tall 5, and once again we're going to measure it. That one's about exactly 25 centimeters long. And if we were being really precise, we'd measure it at multiple places along the length and get all their width and average them together. but we know it's going to tear about in the center, so we're going to get about 5 centimeters there. The width is not as important as the rest of the information. It's really the length that you're comparing. But then we're going to tear this slowly. So I'll tear this as slowly as I can, and we'll speed this up. Now the behavior that you're going to notice is that as we tear it slowly, it gets more length than the fast tears. There's enough time for something to happen in the material. You can't really tell what that is here, but you can tell that it's getting narrower in that center band right here, and it's staying thicker out near the edges. And if I go slowly enough, then that change in the material propagates all the way down, and you can see that it happens in multiple stages as well. So it may happen in multiple places. This behavior is called necking. And you're basically going to describe to us what's happening there and why you think it's happening. And then you're going to have to measure this whole length at the end. Obviously much more stretching than the fast sample got. You'll need to describe why that happened, or come up with a theory as to why that happened, and you'll need to measure the result at the end. So you can use your ruler multiple times, but I went ahead and brought a tape measure. If you're in the makerspace, you'll get those from the cabinet. I'm going to get this as straight as I can. So we got about, let's call it 42.5 inches. And then we're going to convert that 42.5 inches in centimeters.
It's 107.95 centimeters.
Gotcha. So we've got about our 2.5 multiplier right there. Gets us to 108 centimeters. So here's the important measurement, is our length right there. But we also want to notice that the width has changed. So if we just take one sample there, we're down to about 2 centimeters in width. And if we could measure the thickness of this plastic, we would also notice that that had changed. So here's our big difference right there. And then if we go to our percent elongation equation, we're going to do percent elongation equals final length, which is 108 centimeters, over original length, which is 25 centimeters right there. This is for our slow one. And then we'd take an average of that. So for these ones, they'd be averaged together, and for the slow ones, for the fast ones and the slow ones, would each be averaged together. This is going to get us a little bit more than 4. And we'll just check real quick. 108 divided by 25. Yeah, about 4.3. So we're going to call that about 4.3, which is the same as 430%. Now, of course, yeah, so the centimeters cancel out, the dimensions cancel out, and what we've got is a dimensionless number right here. It increased by 430%, more than 4 times as long. There are no units on that measurement anymore. And you're going to get that information for your fast samples in the wide direction and your slow samples in the wide direction. And you're going to get that information for your fast samples in the tall direction, the vertical cut ones, and the slow samples in the tall direction. And you're going to report on whether those are different from each other. And if there is a difference, come up with a theory, not just to the behavior of how it's stretching, but a theory as to why they might be different in the different directions. What could have happened in that plastic, maybe in its manufacture, in its history, in the way you treated them, in the way that they were cut, in the way that they were packaged or shipped. Something may have made them behave differently, or nothing has made them behave differently. You'll come up with that answer. And that's everything.